welcome to Positive Physics. Today we're looking at waves. So I've got a little waving hand to say hello to you. Well, we're not quite looking at those waves or even the little microwaves that you might do with your little finger. Well, we're looking at waves as we look at in physics. But actually our waving hand might help us. If we turn it around, as if by magic, and if we imagine that we have a string attached to the hand, so we'll just attach it through here onto the finger, look, a string coming out, and we attach the other end of that string to the wall, as our hand moves up and down to give the wave, we are going to change where the string is. It's going to move up, it's going to move down, and as it moves up and down, we're going to end up with a wave forming on that string. So actually our little wave has helped us. Here the hand is the source of our wave, the source of the energy, the source of our oscillation. That's just a posh word for vibration, oscillation, but it's a good word to use. And our hand is the source, which is moving up and down and creating this lovely wave shape on our string. And all waves are doing is they are transferring energy from one place to another. So the hand is the source. The source of the energy for the oscillation comes from the hand, or from you if you were holding the string. And then that energy is being transferred in the wave all the way to the wall. So let's try and understand the different types of wave a little further. So imagine you are at a football match, a rugby match, a hockey match, tennis match, you choose which one you want, cricket, anything, okay, it doesn't matter, a music concert, and before the match starts everyone gets a bit bored. So what do? We have a Mexican wave. Now you all know how that works. Okay, so imagine we've got a Mexican wave moving past these people. So this guy has just got to the point where he's put his hands up. All right, so he's just responded and his hands are at the top. And this guy may have met the wave coming in from this direction. So he's just lifted his hands. This guy here has seen that he's lifted his hands or started lifting his hands, and he's got his hands up slightly. This one a bit less. This one has just got the hands down at the moment, not doing anything. This one's bringing his hands down, having been passing the wave on, and this one has the hands up slightly. So what you can see, if I get a different colour, is that we have this Mexican wave is actually the same as our wave that we were talking about earlier. And this is actually an example of a transverse wave. More about that in a minute. Now, there's another type of wave, and it is called a longitudinal wave. Let's give that one written down, longitudinal wave. And to give an example of that, I was struggling to think, how could I give an example of that when I haven't got an animation? I can't really show you. So imagine you've got a line of people, they've all got their feet stuck in the same place. So we could still be at the rugby match, to be honest. We're on the terraces and we're all a bit squashed up together, and we've just stood up to have a look and celebrate the try. I don't know who's scored. But somebody is trying to get through to go to the toilet, and in the process they give a big shove to the person on the end. That makes this person move in that way. So they bump into the next person and they move along that way, and they move along that way and move along that way. But by this point the shove has gone, disappeared. The source of the movement is no longer there. And so this guy will move back until he's back in his equilibrium position. And that just means where you would stand normally or where he started from. This guy has also started to move back. So he's moving back, this one's moving back, and as the wave is continuing along, then gradually people are moving back to their original position. So the movement of each person was from side to side, and the overall, so that's their movement of the individual. But the overall movement of the wave, the energy of the wave has gone in that direction. In the same way that this wave, the energy moved in this direction. I'll just write energy there. Here the energy is moving in the same direction. But the source, what caused it, this great big shove, was along the direction of the energy movement, whereas here the source isn't a shove. Let's turn my arrow upside down because it's not a shove, it's just them lifting their hands, is up and down. Okay, let's look into that in a bit more detail. So we'll go first to the transverse wave and have a go at explaining that. So examples of transverse waves where you get this movement up and down and the energy moving along are water waves. So when you see the waves on the sea or behind a boat spreading out, they're water waves. It's movement of the water is producing these ripples that go up and down. We also have light, and as light is part of the electromagnetic spectrum, magnetic, long word. Takes me a long time to write it. Okay, they're also transverse waves. And finally, there's a type of seismic waves, which are the waves produced in earthquakes, which is also a transverse wave, and they are called S waves. So those are 3 examples. And in each of these, we'll get these areas where we have a peak and a trough. Fantastic, peaks and trough. But there are other words that we use to describe our waves. We use things like amplitude and wavelength. So the first thing, in order to be able to describe our waves more, is we need to draw in, can you remember what it was called when we were doing the shoving motion? The equilibrium position. Okay, so if there was no wave, then the water or the string would be flat along this line. Okay, but because there's a wave, because there's a source of oscillation, it is moving up and down. Okay, so let's put in our source of oscillation. So our source is here. And we'll put that in a different colour so it's obvious. And our source is moving up and down. Okay, so we've got a source moving up and down. We've got this peak and trough being produced around this equilibrium position. Now, the 2 measurements we have are amplitude, which is defined as the distance from the equilibrium position. So that is our amplitude. Now be very careful, amplitude is from the equilibrium position. Some people draw it by mistake all the way from the top to the bottom of the wave, but that's not the amplitude. The amplitude is just from the equilibrium position to the peak. And the other thing we need to be able to measure is something called the wavelength, and that is taken from 2 consecutive identical points on the wave. So it could be, if I draw a line to show where I'm measuring it from the top of the peak to the top of the next peak. So that is my wavelength. Okay. It could also be from the trough to the next trough. That is also my wavelength. finally, it could be from a point where the wave is on the equilibrium position to where the same movement is happening on that equilibrium position. So if you think the string is moving up and then it's coming down, so the string is moving down at this point. Here the string is moving up, so that's not the same point in the wave, whereas here the string is moving down again. So our wavelength would be this distance here. Now how or what units do we use to measure these? Well, amplitude is a distance, so it's meters. Wavelength is also a distance, so it is measured in meters. But sometimes you'll see wavelength given a symbol, particularly when we come to the wave equation, which we'll do another time, and the symbol for wavelength is lambda. It's like an upside down Y. Okay, it's a Greek letter lambda, and so you'll see that, we'll come on to that again, but that is what the wavelength is. Now it's really important that you can define a transverse wave correctly. And the transverse wave is defined as the direction of, okay, our source, which is the source of the oscillation. So the direction of the source, the direction of the oscillation, the direction of the vibration, but oscillation is the best word to use, is perpendicular to the direction of energy transfer. So here our energy is being transferred in this direction. The source is moving perpendicular to the direction of the energy transfer. And remember that what's providing the source isn't getting up and running along to take the energy with it. The source is here providing the oscillation. The energy is being transferred in the wave. Bit like when you're doing a Mexican wave, you don't get up and run round to the end and start again to transfer it on. That would be transferring the energy in a different way. You don't run with your arms going up and down. You literally just stand still and move your arms up and down. Okay, you didn't see that. I was doing the actions here. I forgot you can't see me. Right, okay. Longitudinal waves. So we've got transverse, where the source is moving perpendicular to the energy direction. Longitudinal waves, examples of those then are sound. And again, if we look at seismic waves, we have seismic waves called P waves. Okay, primary waves. And the way to think about this, so I've got a little picture of a trumpet here. Imagine the sound being produced. This is a bit like the shove situation. The sound is coming out of the trumpet, and if you imagine that dots on my paper are molecules of air, when the source, the sound wave, moves, it pushes the air, and these air molecules vibrate, and in that vibration they transfer on the energy. And what you end up with is areas where the air is really, really concentrated together. So you end up with high pressure. I mean, not sort of pressure that's going to burst your eardrums. I suppose it depends how bad the playing is. And then you end up with areas where the particles have moved apart in the process of transferring. And then some areas where, because they've moved together and they're all concentrated. And you often hear longitudinal waves or sound waves described as pressure waves or compression waves. So here we have compression of the air particles, the air molecules, and that is what's transferring the wave. I'm going to stop drawing this, otherwise I'll be at it all day. Okay, we have different regions. So here we have an area, and it's called rarefaction. That just means the molecules, the particles have been spread out. And here we have compressions. All right, so we have compression area, rarefaction. And again, we need to label the wavelength. And the wavelength, just like before, is the distance, so it's measured in meters, between two identical areas of the wave. So here I've drawn it between two consecutive compressions. And remember that the wavelength has this funny symbol, lambda. Okay, so we get these compressions. And what happens to those compressions is when they reach your eardrum, they make your eardrum vibrate, and that's how we hear. So now, if we think about the source of our vibration, in this case, it's moving backwards and forwards. The sound wave is this is the shove situation. The source is moving backwards and forwards, which is producing these areas where the particles are compressed together and then moved further apart. And also, if you think about it, if the trumpet is here and your ear is here, there we go, which way is the energy moved? Well, it's moved in the same direction. So the direction of, remember that special word, oscillation, is, in this case, parallel to the direction of energy transfer. So with transverse waves, the direction of oscillation is perpendicular to the direction of energy transfer, and here in longitudinal waves, the direction of the source, the direction of the oscillation, the direction of the vibration is parallel to the direction that the energy is being transferred. Now, where does the energy go? Well, sometimes it just spreads out into the surroundings. So if you imagine, if you were stood one side of a very large field and you shouted across to the other side of this very large field, the chances of somebody hearing you are quite slim. And also you've got problems with wind as well, so we won't go into that, but they couldn't hear you. That energy, you'd still produce that sound energy, but it had spread out in all directions, and it had got to a point where it was too small or too little energy to be detected by somebody's ears, the other side of the field. But when waves reach a solid object, there's three things that can happen. They can either be absorbed. Okay, so let's think of a sound example of that. Imagine you've got some really great soundproofing foam. When the sound reaches that foam, it is absorbed. The energy is absorbed by the foam, and what you'll find is that energy has been transferred into another form, usually thermal energy, which will then be dissipated to the surroundings. So the energy hasn't disappeared. Remember, energy is never created or destroyed, it's just transferred into other forms. So the wave energy, the sound energy, when it reaches a solid object, or light energy, can be absorbed. All right. It can also be transmitted. So as I'm writing this, we're in lockdown, we're all living in our houses. I would imagine you can probably hear conversations from the next door room, even though the door might be shut. That's because the walls have transmitted the sound through them. And the final thing is that you can get reflection. So it could be reflected. So that's how echoes occur. If you go somewhere where there's an enormous great wall in front of you and you stand maybe 20, 30 meters away, you can clap your hands and you will hear an echo. That is the reflection of the sound from the wall. For our light waves, we know we get reflection in mirrors and from surfaces. You can see reflection here of my hand. I mean, it's like a shadow, but actually that's a reflection of my hand in the surface here. We know we can have reflection. And there's one final thing that can happen in the transmission process, and that is that the waves can change direction. Now that is if there's a change in density of the medium they're travelling through. That's called refraction, and we'll talk more about that another time. Thanks for listening. I hope that helped. Bye.